All right, let us see the demo of this 1-bit full adder using two half adders. So on desktop, you have this shortcut model sim Intel FPGA. So you just double click that. So once it opens up like this, you can start, this way also by clicking on jump start and create a project, or you can just close that one. The moment when you have to click this one, I just close this. When you double click this model sim Intel FPGA, this jump start, instead going to this, you can close and you can start from file. Go to file, new, and then here project. First, you have to create the project. Very first step is go to file, new, and then project. So it will prompt you. This operation will close the current project, but the default last project, whatever you have worked, that will be opened. So when you are trying to open the new project, it will try to close the earlier existing project. So click yes. Now here type the project name. So our project is FA full adder. FA stands for full adder, 1-bit. So here you should not be giving any spaces like, for example, FA space 1-bit. So like that, don't give the space. You can use underscore, but no spaces. Okay. So I'll be using FA 1-bit. And then this project location is also important. So default, whatever the path it is showing, don't take that. Go to browse. And then you create your own space where you want that project to be. So I am planning here on my desktop. I have created a folder called the lab demos. Here, lab demos. So open that. Inside that, create a folder, new folder, create new folder, name it. So what is that? My project FA. FA, that is full adder. Select that one. Select folder. So now that is the path here. The path is now changed to on desktop lab demos in that FA folder. In that FA folder, this FA 1-bit related stuff will be there. And the other two things default leave as it is. Click OK. So once you have done, then it will prompt here add items to the project. So close this one here. Go to file again. New. Here. Go to source. I repeat again. File. New. Go to source. Here. Click on Verilog. Not system Verilog. Not VHDL. Not any other. Here. Do and other. Only Verilog. So now it will open up here editor. Here you have to type your code, the design file. So what is the design file? Module. We have HA, first half adder. In that A, comma, B, comma, sum, comma, CO. These are the port list. All right. Now type declaration. Input A, comma, B, semicolon. Output sum, comma, CO. Now here in any level you can describe here. There are various levels, right? So we have switch level modeling. And then we have gate level modeling. And then we have data flow level modeling. And then we have behavioral level modeling. And then we have switch level modeling, gate level modeling, data flow level modeling, data flow level modeling, behavioral modeling. And then finally we have uh, what is that called? The structural. So in any way you can write logic here. In either of these methods, you can write the logic here. And then finally you have to write the AND module here. So here we will be using this gate level modeling. So as discussed, we need one XOR gate. Syntax is open the parenthesis, first output variable followed by the input variables. Next, we need one AND gate. Syntax is again same, open the parenthesis, first output variable followed by that input variable. And then AND module. So here you can see note asterisk this star here. After default here, you are seeing one star asterisk. It means this file yet to be saved, not yet been saved this one. We have to save this one. To save this one, click on this icon, save icon. Then it will prompt you like this. Give here proper name here. Keep the .v as it is. Remaining thing you just remove. And this is since half adder. So just give HA. Relevant name you have to give without spaces. And now go to this file again. Go to new, source, Verilog. So now we are going to write full adder. So module, FA. FA has got A, comma, B, comma, C in, comma, sum, comma, CO, port list. And the type declaration here is input A, comma, B, comma, C in, and output sum, comma, CO. Now we only have to instantiate this half adder that we have written down. So HA-INS1, that is this INS1 is the instantiation name. Now, what is that we want to bind with this half adder? We want to bind here A. This INS1 is the instantiation name. Open the parenthesis. First pass A, comma, B. A and B you pass. So this half adder going to produce sum and CO. So let's capture them in S1 variable and C1 variable. Now next what we have to do one more time, we have to instantiate half adder with another name. Now what we have to pass, this S1 and Cin we have to pass. So what it is going to produce? Sum and C2. Next, what we have to do? We have to instantiate primitive or with the or keyword. And what it is going to produce? CO it is going to produce. So what it is going to take? C1 and C2 as inputs. So that's all we have done. And then we have to close with the end module. So this exact thing, we have discussed here. So this is how exactly like AB been passed to first half adder and it has produced S1 and C1. And this S1 is passed to next half adder along with the Cn. It is producing S2. This S2 is nothing but directly this sum. So we are using sum. And then second half adder is producing C2. The C1 produced by first half adder and C2 produced by second half adder, both are given to OR gate. OR gate is producing this carry out. So this is what we have done. Yeah. So now this also needs to be saved. Click on this save. So same dialog box will come. So just remove this untitled name and give FA, that is for full adder. And dot will don't remove that extension of that file. Just remove the title of the file. So save. So now what is left? We have to write the test bench. So click again, file, go to new, go to source, go to Verilog. Here you have to write backquote or backtick. This is also spelled as a backtick. Time scale 1ns/1ps. This is system, this is compiler directive. What is this backward time scale? Backward time scale is a compiler directive. Compiler directive. So it tells the compiler, it helps the compiler to treat this one here. Like you have, just a minute, let's remove this. So you have simulation running from 0 time to some 100 nanoseconds. So this is the scale, let us say, this is the horizontal scale. On this scale, what is the time unit here? You have different time intervals. So what is the time unit here? That is what this is telling here. Like in the code, you are going to use some delays. Let's say you are using #5. So this delay, is it in milliseconds? Is it in nanoseconds? Is it in seconds? That is what dictated by this time unit. And the time precision is after this integer, if you have any fractional part, decimal part. So this, how many digits are there? Like, let us say you have some few more digits here in the fraction. So, but this time precision, what it does is it limits the precision. Here, 1 picosecond is nothing but 0.001 nanoseconds. So it tells that on this nanosecond, when you are considering scale as in nanoseconds, on that, after decimal point, only 3 digits needs to be considered. So here, how many digits we have? 73578, only 3 digits. So that is dictated by this time precision. The first one, remember, it's the time unit. The second one is the time precision. So now here we have to write the test bench. module tb underscore fa. Put the semicolon, and this will have somewhere down and module. Now, in this full adder, this variables with the keyword input, they will become reg in the test bench. Copy them, get them here, paste it. So these input variables will become the reg data type, reg, reg. And this output variables, copy them, they will become wire. They will become wire data type. So now you have to instantiate the module that you want to test. This is the module that we want to test. Copy, get it here, and then create a space here. You have to use some name. I am using TUT, design and test here. Now, initial. This initial is called a procedural construct. So in this procedural constructs only we can use loops, conditional statements, all that. So this initial is a keyword, then begin. This begin will have somewhere end. So put the end. Now here I have to generate this A, B, C, right? So if you're generating this, you have got this A, B, C in. So obviously you start with 0, 0, 0, and you go till 1, 1, 1, right? That is 0 to 7, right? So then we have to produce here. So how do we produce? Let's see that. So here what I'm going to do here, I'm going to use for loop for open the parenthesis. Inside that, I equal to 0, I less than or equal to 7, I equal to I plus 1. Here begin and end. Each whenever you are writing begin and I mean you need begin and end, then at the till end you don't wait. First you put these enclosures begin and end so that in case if you're forgetting, then that will be problem. So if you initially only if you write, then you will not be missing this end. That way you can avoid any mistakes. So now here what we have to do, we have to use the concatenation operator, that is this braces, put inside A comma B comma C in, and then assign this I to that. So what happens is when let's say I when it is like 6, when you are trying to assign to this concatenated A, B, C in, this 6 is internally converted to binary like this. So this 0 is assigned to C in, this 1 is assigned to this B, this 1 is assigned to this A. Like that, assignment is done. Now, after applying one value, we have to give some delay with the delay control operator. Hash is a delay control operator. So that's how we are giving the inputs here. So after this, once this is done, here you just have to stop the simulation. Hash y. There you can stop the simulation at that delay. After that delay, dollar stop. So what happens is, once it enters this loop, 0 is assigned here, then delay is taken here, hash 5, I mean 5 time unit delay. Then this loop is iterated. It will be like incremented 0 plus 1, that is 1. And this is condition test is done. When it is true, then it will enter inside the loop. Then it will apply this one to this ABC in. And then again, it will take the delay of 5 like that till this loop condition is satisfied. It will be happening. Once it comes out, it takes additional 5 time unit delay, and then it stops the simulation. So note that here we are not having any statement which will display in the console. This is called the console area. So this will be showing up in waveform window. So let us see how it is happening. So first we have to save this one. Click on this save button. Now give appropriate name. That is TB underscore FA. So we are testing FA. So TB testbench underscore FA dot V. Save. Now, if you see this project area here, this project, that is fa1bit, we do not have any files here added to the project here. So right click here, this area, right click, add to project, existing file. So browse, you have created this folder, right? FA folder. Inside that, you have saved all of these files created. So select all of this, open, and click OK. So now all files been added here. Sure. So to compile, go to this compile, compile all. So if there are any errors, it will show up errors like this, the way it is showing up. Sure. It is saying FA successful, HA successful, but TB failed with one error. Just double click this, it will show up what is the error. Sure. It is like TB underscore fa.v is the file. In that line number 12, there undefined variable I. So at line number 12 somewhere, undefined variable I. So we have to define this I here with the integer I. Now save again, compile again. So now you can see all these are successful. So once this is done, go to simulate, start simulation. Now locate where your work folder is. Among these several folders, you have to locate this work folder. Sometimes it will be up the way. In my case, it is. Sometimes it will be down here somewhere, work. So you have to locate work folder. This plus sign is there. Now expand that one. Select your Testbench module name. This is my Testbench module name. So select that and click OK. So after that, you have to wait till you get this sim underscore default. You have to, it will take 1 or 2 or 3 seconds. So once it is settled down, you will see this sim underscore default window. There, your test bench module name is shown up. Right click that one, add wave. Click on add wave. So you'll be seeing here waveform window. And now you go to this one, like run, we have to run the simulation from here. And here it is like default 100 picoseconds, but we have to run in nanoseconds. So remove the T, and then just beside that there is the run button. Click on that run. So now you cannot see here in the console. The results you cannot see in the console because we did not add anything in the test bench which will help us to show in the console. So we have to go to the wave here, this wave, this here. Now you click on this zoom full. So you can see the waveform here. Click anywhere here. So this vertical bar wherever it is. Corresponding to this, the values are seen here. A is 0, B is 0, C in is 0. So your sum and CO state, these are the states are 0, 0. So when you move, I mean, at different place, when you click, you can see your A is 0, B is 0, C in is 1. So sum is 1 and carry out is 0. So like that, you at different time intervals, you keep moving this way and ensure that your results are correct here by checking this way. This is very much essential because in exam, like explain the waveform means you cannot say that see something I got here. You have to explain this way by justifying, like you go to one time interval like this and show the values here, like corresponding values for A, corresponding values for B, corresponding value for C in, and what is the intention of this design, that is one bit full adder. According to that, are you getting the expected output? You have to explain that, like 1 plus 1 carry out is 1, sum is 0. That 0 plus 0, again this sum is 0. So you are getting it. When you go to this condition, like where A, B, C in all are ones, then your sum is 1 and your carry is 1. So you should able to explain. With this explanation, you are justifying that your design is correct. Your test bench is correct, your design is also correct. So that's how this is the, I mean, you do the simulation, and to stop the simulation, go to simulate and simulation. So are you sure you want to quit simulating? Yes. Now I will show how to display in the console. To show in the console, you have to do one thing here in the initial block. After begin, you have to add $monitor, $monitor. Open the parenthesis. Inside that, what is that you wanted to see in the console, you put that one inside the double quotes. I want to see A. In which format you want to see A? In binary format. So percentage B. That is a format specifier. B variable I want to see in binary format. Percentage B. This B and that B is different. This B is our variable. This percentage B is the format specifier. And I want to see my C in which format? Percentage B format. So similarly, I also want to see my sum and carry out in binary format. So sum and carry out. This is for our, in the console, that's how it is going to put the display A equal to B equal to C equal to this column, then sum equal to CO equal to. But corresponding to this B, we have to put here the variables also. This percentage B for format specifiers, we have to put A comma B comma C in comma sum comma CO. Now, if you wanted to see the simulation time, then you have to put additionally here. Let's say at time, at the rate time. This is for my purpose at the rate time. And this is the time format specifier, percentage G. And this since I know that my scale is in nanoseconds, whatever it is going to display in nanoseconds. So this NS is for again for my reference. And this colon is also for my reference. That's how it is going to present. So this colon is also for our purpose, like how well we want to put in display. That's how I am putting the things here. So now corresponding to this percentage G, I need one here variable. The way variables are there, but something needs to correspond to this percentage G also. That is in the dollar time. So this dollar time is a system function. What it does is it returns the simulation time. So that's how it is. This is going to help us to display here in the console. So save this one. You have to compile again, compile all. So once you are like no errors, then go to simulate, start simulation. Again, go to this work folder, expand this plus, select your Testbench file, click OK, wait till that sim default comes. Now this time if you don't want to see, I mean in the waveform here, those because you added anyway the you know things to be displayed in the console. So directly you can run here. So things will not be added up to the waveform. So like this, run in the console, things are displayed. In the waveform, it will not be there because we did not add, right? Selecting this way, add wave, we did not do that. So these variables are not added to the waveform window. But how is that it is displaying in the console? Because of this statement, $monitor statement. Okay. So from here also you have to justify, like if you are talking about this time interval, then you have to say, because A is 1, B is 0, so expected is sum 1 and C carry out is 0. So expected is coming. So like that you should be able to justify your result. So that completes this experiment. That is 1 bit of full adder using 2 half adders. So remaining I will do that. So kindly practice this. If you have any doubts, reach me out.